Hey everyone, it's David with the AstroDNA Observatory, and I'll have to say that this has been some pretty crappy weather here at the end of January. The last 10 days or so, we really haven't had any chance to get any images done, so essentially the observatory is somewhat out of commission, and that's okay. You know, this happens. It's part of this hobby, and, we need to make the best out of the time that we do have when we're imaging, and that means that I like to take these downtimes to properly plan for the projects that I have in mind. And January is typically a tough month, at least where I live. I live in the Northeast and north of New York City by 60 or 70 miles or so. And knowing that it was going to be a tough month, I chose a constellation to focus on that has Gemini, which has, really only has a handful of deep sky objects, but they're very interesting. In fact, these last few videos I've covered several of them, including M35 and some of its neighbors, other open clusters around M35. We did the Medusa Nebula, which almost destroyed my rig, jokingly. But that's a planetary nebula, also in Gemini. And then we got some partial data on the Jellyfish Nebula, which is a supernova remnant. And if you recall in that video, I was really excited with the hydrogen alpha that was presenting, but I also realized that this supernova remnant is larger than what the AT115 EDT is able to reveal. The field of view with the ASI, even with the ASI2600 and the 0.8 reducer, we're just not getting the complete supernova remnant. And but I love the detail that is being presented with this scope, and so with that, I'd like to do a mosaic. In fact, I have two project goals remaining for Gemini, which is unlikely I'll be able to complete them in January, so they'll probably overlap with my February projects. But one of them is a mosaic of the northwest corner of the Gemini constellation, where the Jellyfish Nebula is the supernova remnant. But I want to do it in a way that also captures M35, some of the other open clusters, and some other features that we have in that sky, including a couple of prominent stars at the heel of one of the twins. So I have a beautiful vision for what I'd like to do, and I'm going to share all of that with you today. We're going to plan out this mosaic, and I'm going to show you how easy it is to do it with N.I.N.A. But I also have another project that I'd like to get done. You folks may be looking at the contraption behind me, and this happens to be one of my medium format film cameras. It's a Mamiya RB67 Pro camera. I have a couple of these bodies, as well as some Hasselblads and several other medium format cameras. And I used to shoot film, even for my astrophotography many decades ago. And as I was organizing during this down period, I pulled out these camera bodies and I said, I want to get some very wide field astrophotographies, nightscapes of the constellations that I'm focused on each and every month. So I want to get Gemini, as well as its border with Orion, and I want some very wide field astrophotography work done. So I'm going to actually shoot some medium format film. And I'm going to compare that with some work that I'm going to do with a full-frame digital camera, my Nikon Z7 II. And I think it'll be very interesting to compare these, the outcomes from these two approaches. So hence I have the Ioptron SkyGuider Pro set up with some guiding, and this is going to be a lot of fun if we get the weather for it. So at any rate, look, if you're into this type of content and astrophotography and astronomy, go ahead and subscribe. I think you really enjoy the videos that we're producing here, and I think you'll enjoy the community that's forming. And with that, let's get into how easy it is to do mosaics in N.I.N.A. So grab a piece of paper and a pen if you're so inclined, and let's step into it. So what is a mosaic, and why do we create them in the first place? Well, Simple. A mosaic is an image that is formed by stitching together two or more other images. And the images themselves, we refer to them as panels. And the panels are typically organized into rows and columns. And for example, let's take this image of the Bubble Nebula. Now, I shot this with my C8 at a focal length of 1280 millimeters, and I was using the ASI 1600 millimeter, MM Pro sensor. And as you can see, it fits very nicely. Actually, there's a little bit of a crop on this, but it's a beautiful composition. But let's pretend for a moment that I was shooting with a much longer focal length, say the native 2000 millimeter focal length of the telescope, so I was not using a reducer, let's say. Or if I was using a much a larger aperture scope with a much longer focal length, like a 16-inch Schmidt-Cassegrain telescope. In those cases, the field of view of the rig would be reduced significantly, and we wouldn't be able to fit the target on that sensor, on the 1600 millimeter sensor. So I would either have to change my rig up, or I could plan a mosaic. And so here's an example of a fictitious 9-panel mosaic for the Bubble Nebula. It's fictitious because it's assuming some kind of rig configuration that has this field of view that matches the illustrative panel sizes. And we'll talk more about that and how to determine the field of view for your rig and how that translates into mosaics, panels in your mosaic. We'll do that in a moment. But for now, just appreciate that this example mosaic is being formed by stitching 9 panels together. There are 3 rows and there are 3 columns. And note that there's an overlap across these panels, which you need to ensure that you have the data, no gaps, necessary to register and align these panels into one single image, the mosaic. Now, it should be clear that, we create mosaics because the target is larger than the field of view of our rig, but that's only part of it. I mean, technically we could get a setup like a DSLR with a telephoto lens and point it at the object, and we can get a much wider field of view and capture it. But in that scenario, we're losing detail. When you do a mosaic with these longer focal length rigs, what you're doing is you're actually capturing the target with intense detail. And really, what I mean by that is that the resolution of your sensor is preserved across the entire area of your mosaic. And the net result of that is like very, very detailed. Let's call them sky surveys, creating your own personal sky surveys with awesome levels of detail that you can zoom into and reference in ways that you really can't do if you were to take a very wide field shot with even a full frame sensor, for example, on your DSLR. You just simply will not be able to zoom into the level of detail that you can with your mosaic. And with that, let's move into a discussion of the mosaic that I am planning. Okay, the very first thing we're going to do before we jump into shooting a mosaic is make sure that we understand the field of view of our rig and how that field of view is going to scale based on the composition of our mosaic, meaning the number of panels that we have planned for the mosaic. And to do that, there are a number of free tools on the internet, including, I think, astronomy.tools is one, and I'll share that here. But I've also created a very simple spreadsheet, which you should feel free to follow along and create your own. That is very useful for me, at least, when I'm planning out a mosaic. Now, as I mentioned, your field of view is a function of your rig, meaning your optics train, meaning your telescope, as well as the camera that you're going to be imaging with. And you can see here in this spreadsheet that I'm working with the ASI2600MM Pro camera. And you can get a lot of this information is simply published by the manufacturer of your camera. You should determine how many, go find out how many pixels are there, how many pixels wide is the sensor, and how many pixels tall is the sensor. In this case, it's 6248 is the width in pixels and 4176 is the height in pixels. And you also should determine the pixel size. And generally speaking, these pixels are square. So 3.75 micrometers is the pixel size for this camera. Now, it's also important to know the focal length of your telescope. And in this case, I'm using the AT115 EDT for this Mosaic, which has it's 115 millimeter aperture, and I think it's a f7 natively, which will put it somewhere in the 805 millimeter focal length natively. Because I'm using a reducer, a 0.8 reducer, that brings the effective focal length down to 664 millimeters. And given that information, the resolution of the rig, meaning the camera and telescope combination, is about 1.2 arc seconds per pixel. Okay, and I'm going to show you where the everything here is published by the manufacturer, or you can calculate easily. Perhaps the trickier one is the resolution. But you can. This is where we'll take a peek at astronomy tools. So it's astronomy.tools, and there are some calculators there, including a field of view calculator, which you see field of view. You can select imaging mode, and for the purposes, of my Mosaic, M35 is one of the objects that I like in my Mosaic, so I've chosen that, and I specify the Astrotech telescope. As I mentioned, a native focal length of 805. Its aperture of 115. This is all filled in automatically. And then I selected the camera, the ZWO ASI2600. All this information is filled in automatically by this utility. Very powerful utility, very nice utility, convenient. By the way, again, all this information is available from your equipment manufacturer as well. This is just a convenient place that you can kind of put it all together for some calculations. So there's also a reducer. You can specify your reducer. I'm using the 0.8. And from that, and I'm, of course, at 1:1 binning. So all of that is used to then go ahead and calculate the resolution of 1.2 seconds per pixel. And it also calculates the field of view. And that information is also present in this in my spreadsheet. So you can get the 1.2 value, the resolution from astronomy.tools. And actually that information can then be used to do your own proofs on these field of view values. So this sensor with this telescope has a field of view of roughly 2.09 degrees in the X direction and 1.4 degrees in the Y direction. So we can prove that, by the way, with a simple multiplication of the number of pixels that we have times its resolution. So 6,248 pixels at 1.2 arc seconds per pixel, and divide that by 60 seconds and then 60 minutes to get degrees. 2.082. They've rounded that to 2.09. Same exact calculation can be done in the Y direction. Trust me when I tell you this is important, just to know the math here, okay? And we can then go ahead and further prove that we can calculate the actual dimensions in millimeters of the sensor itself and validate that against the website, the ZWO website. This is simply the number of pixels times the pixel size, and that gives us our sensor of 23.43 by 15.66 millimeters, which we know to be the APS-C format. Okay, so this is what one frame or one panel would look like if we had a one-panel mosaic. This is what the dimensions would be. But we know that we're going to be using we're going to be stitching together multiple panels. So, and we mentioned that the panels will be organized by columns and rows. So the columns will determine the width, the number of how many panels do we want to make up the width of our mosaic, and then the rows will be the height. So, but there's one other piece of information here. Notice how if I said in my example, I'm saying a 3x3 mosaic, that the field of view of the mosaic is not equal to 3 times the field of view of one panel. And that's because there's something called an overlap. And typically we plan an overlap of 10 to 20% in a mosaic. That allows for registration and alignment so that we can actually get data and no gaps in our data in between these panels. So in this case, I've planned on a 20% overlap for each panel. And with that, there's a formula here that I've put together. It's a relatively straightforward formula, but it's essentially to calculate the field of view in a multi-panel mosaic. It's going to be equal to the field of view of one panel plus 80% of the field of view of all the other panels. Okay, so if you can imagine stacking, if you stack these panels side by side, if you had one panel, it would be the field of view of your basically your sensor. As soon as you go to a second panel with an overlap of 20%, it's going to be equal to the original panel plus 80% of the second panel. And that will extend out in a series, to no matter how many number of panels you have, it'll always be equal to the field of width of one panel plus 0.8 times the remaining panels, the extra panels that you have. So at any rate, it's a relatively simple formula. You can see it here, and hopefully that makes sense. So with that, why is that important? Well, now that tells me that the mosaic that I'm taking is essentially achieving a 5.4 degrees in the horizontal, meaning across the columns, and a 3.64 degrees in terms of its height or its rows. And I can then take that and reverse engineer, well, what is that the equivalent of in terms of pixels? So that's really like as if we had a sensor that was 16,300 pixels by 10,920 pixels. And if we would then go ahead and kind of abstract that out and say, well, what would that be in terms of dimensions of the sensor? It's about a 61 millimeter by 40 millimeter sensor. Okay, and that's important because these values can then be used in your planetarium software and other software to create custom views on your sky charts. And let's take a look at an example of that here. So this was what one sensor would look like focused on M35 at its center, and that's based on the ZWA, the properties that we know of for the ASI2600 camera and this telescope. Well, if we now take a look at what if we plugged in an imaginary camera, a custom camera, where we plugged in the resolution that we just calculated, number of pixels X and Y. The pixel size is the same, and so is the resolution. But what has now changed is that our field of view is the mosaic field of view, and with M35 in the center. And now we see, this is not the way I will frame it. I will show you an example of how we will frame this in a moment. But now we see the full size of the mosaic, and this allows us to get a sense of what the composition can look like. Okay. In fact, let's take a look at what exactly it will look like when we plan out our image in N.I.N.A. And here we go. So this is N.I.N.A, and we're going to get to this in a moment now. But just to give you an idea, this is that mosaic, right? And this is M35. And here is the supernova remnant, the jellyfish nebula, and a couple of very important stars. And we're going to talk about this next. Okay, so it is the 29th of January, and so a couple days into making this video, and there's a possibility that the skies will clear tonight for a little bit of imaging, and that means that there's a chance that we can get at least a sketch of this mosaic complete. And that means we really got to get our planning right. So I'm going to show you how I do it. And we'll do it together right now. In fact, I have Stellarium up and running, remotely connected to my observatory computer. And a little orientation. I have the time set for around 6 p.m. this evening. Just so everybody's clear, here's our north to south line, which is of course, our meridian. We have our east to west line, which is, of course, our equator. And we know that Gemini, we can see Gemini. I have the constellations being shown here, but I'll zoom in a little bit for everyone. We have our constellation of Gemini with both Castor and Pollux here. And so here are our twins. And as I mentioned, I'm most interested right now in Castor's heel, and actually let's just call Castor's left foot. And if we kind of just use Stellarium to zoom in there and note that field of view is now at 18, but why don't we bring that down to something closer to, let's say, 6 or 7. And so now all of a sudden we have a field of view, and we see M35. We see some satellite open clusters around M35. And we also see IC443, which is the jellyfish nebula, supernova remnant. I've got boundaries turned on, so this is the northwest edge of the Gemini constellation, and then we move into Orion. And in fact, the Monkey Head Nebula is over here. Do not get distracted by that target. That's not what we're interested in. But we can see that with a field of view in and around that probably 6 degrees, 6 degrees, we're going to be able to frame M35 as well as IC443 and some important stars like Tejat and Propus, as well as a number of other interesting deep sky objects in this area of this constellation. So what I'm going to do actually is, for the sake of it, I'm going to make sure that I have selected one of these objects, because we're going to pull this object in, and we're going to use, actually I'll select the star Propus. And so what I'm going to now do is switch over to N.I.N.A, which is here. And N.I.N.A, of course, has its own star sky atlas, which you can always query on different objects by their designation. So for example, I could search for M35, and M35 will appear, and I can add this to my framing assistant. I can search for IC443. And so there's another example. Now, we could simply send this to our framing assistant, or since we've already pulled something up inside of Stellarium, right? I've already got something in focus, Propus, the star Propus in focus in Stellarium. Why don't we go ahead and go to the framing wizard, the framing tool, and why don't we pull in that star, Propus. And notice that I am using, so the way that this works is that there's some sky survey that's going to supply all of the images for your framing assistance. I'm using the NASA Sky Survey. There are a number of other sky surveys available through N.I.N.A, and I think you might even be able to register more. I'm not sure about that. Don't quote me, but I like the NASA Sky Survey. Now, it takes a little time. It's going out and pulling out plate information. But you'll notice here that I can also indicate, it's pulling in Propus from and the coordinates from Stellarium, but I'm telling it what field of view I want it to display in. So now we see that Propus is centered in my frame, but it's showing an 8-degree field of view from the NASA Sky Survey, which is absolutely awesome. And that allows me to play around with framing by dragging and dropping. Now, I'm gonna, before we get into this, I right now you can see that I have set up this camera information is pulled directly from my setup, and this should be familiar to everybody. These are the pixel dimensions of the sensor, as well as the size of each pixel and the focal length of the rig. No different than the spreadsheet. Now, in the target area, you'll see that I have specified panels. I'm going to decrease these panels for a second. Note, as I decrease the number of horizontal and vertical panels, the framing assistant is adjusting automatically. So let's go down to a 1 by 1. Here's a 1 by 1, and theoretically I could frame this and get a good part of the most of the Jellyfish Nebula in one frame. But as I've indicated, I really want to increase that, and I want to get some of the other surrounding objects. So here I could do this, and now all of a sudden I can frame and I can get not only Jellyfish Nebula, but I can get 2 very important stars in Gemini, some additional nebulosity, and an open cluster. But what if I go to 3 by 3? If I go to 3 by 3 and just a little adjustment of my framing, and now I've got what I think to be a very compelling composition here, which includes M35, its satellite open clusters. It includes my Jellyfish Nebula, several key stars in the constellation. In fact, all of the Gem 1 through, I think Gem 1 through 9 or 10 are included here, meaning this is just a numbering system for the first 10 stars from the west going east in the constellation. But more importantly, this is feeling like a very fascinating, very really very well balanced and interesting composition. Now, as I'm moving this around, right, you'll notice that the mosaic panels themselves, the coordinates of each frame are changing. N.I.N.A is automatically handling this information for me, determining what the RA and DEC values are for these panels. And each panel is labeled 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. So what's actually happening here is that N.I.N.A is preparing for a session where nine frames will be composed and imaged. And so notice that there's also this panel overlap. I did my calculations using 20, but I could reduce the overlap of these frames, and that will widen my overall field of view, but it'll bring the risk that we'll have difficulty registering and aligning this mosaic. So let's leave that right at 20%, and because I think it does a great job of capturing what we want. And I'm going to move this. I'm going to try and get a framing that I am satisfied with, because we are going to try this tonight. Whether it's tonight or the first clear night that we get, we're going to shoot for this composition. Now, there's a rule of thirds, but at the same time, I also try to avoid. I'm going to try to avoid my heavy subjects in the overlap regions, but unfortunately that's not going to be doable here, which means that we risk that some of the overlap regions, we have to make sure that when we do the alignment, and we'll go over this in a different video, that we handle any gradients, and there are techniques that we can use when we stitch these things together. So I'm going to settle in something like this as my image. I'm satisfied with this. So again, and we're going to do a first sketch of this with first light opportunity that we have, and really to do this, all we're going to do is add this to the sequence, and we go to sequencer, and we're going to go to a deep sky instruction set, and there we are. So I'm going to for now, I'm going to remove, this is Propus panel 1, let's take a look, panel 2, good. So this is exactly what I want. So this is instruction set here needs to be removed. So this is from a prior, when I was doing some comment work. I'm going to delete that. And now we have, for each, we have we have our deep sky sequence that for each of the 9 panels, we have a set of instructions. Now, I am going to say that this is where, planning is really important. The very first thing I'm going to do is I'm going to save this as a new target, and we're going to call this, we'll call this West Gemini for the sake of it. So we could also call this Caster's Heel. Maybe we'll do that, Caster Heel, and then save. So, and then we're going to continue to make some adjustments here. So the very first thing we'll do is we'll open up, and because we're going to shoot the same channel each time that we run a sequence, we're just going to concentrate on one channel at a time, but we might as well just have a global trigger here that whenever we have a filter change, we're going to do an autofocus. So that's a global trigger here. The other thing we're going to do is for each of these guys, let's take a look. For each of these guys, we're going to add an instruction here, which is should automatically slew in center, but let's go ahead and do an instruction set, which is the telescope slew in center. Okay, so it's going to, that's the first thing it's going to do. And then right now what we're going to do is we're going to shoot entirely luminance as our sketch, and this is going to be a camera instruction, and we'll do a smart exposure. And we're always going to be shooting here. When I shoot broadband, I don't use any gain. I use a gain of 0, offset of 50. But we're going to do 30-second exposures using the what is the IR UV cut filter or luminance. And we might as well go ahead, and I usually do it every few frames. Okay, so this set of instructions we're going to repeat for each of these, and then we're going to resave our sequence. Okay, so we've got everything set up. Let's just do a quick double check here to make sure that we are doing a slew in center, then doing 10 exposures of 30 seconds each on the IR filter, dithering every 3. Panel 1 looks good. Panel 2 looks good. Panel 3 looks good. If I change the dithering to 3, this is why it's important to always check your work. This is monotonous. It's monotonous, some of this stuff, and it's easy to make mistakes. Dithering every 3, 1030 looks good. Panel 5, IR 3, 1030 looks good. Panel 6, 3, IR 1030 looks good. Panel 7, 3 IR 1030 looks good. Panel 8, 1030 IR dithering every 3, and finally panel 9 looks good. 3 IR 1030. Okay, with that, what we're going to do is we're going to actually save this out, and this is going to become our caster heel IR. And I do this for a reason, because we're going to do this for each channel eventually. Okay, with that, we have our sequence ready to go, and that sequence can, of course, be run when we're ready. We'll go to our imaging tab, and we'll go ahead and we'll load that sequence when the time is right. This, for those who are curious, if we're shooting, think about it, if we're shooting 10 30-second exposures, that means that about 5 minutes on each panel, and give or take, let's call it a minute of transition in between. So, let's say that this is a 1 hour session, all using the IR UV cut filter or luminance data. And from that, we should be able to stack that all together and take a look at what our composition will be. All right, very good. That is how we set up N.I.N.A for a mosaic. Okay, folks, it's time to call a wrap on part 1 of the Mosaic video series. And hopefully this video helped to demystify what a mosaic is. It shows you how to plan for your mosaics based on the field of view of your rig. And it shows you how to easily translate those plans into a multi-panel sequence within N.I.N.A. And if we're lucky and we have clear skies for at least 1 hour tonight, just 1 hour of clear skies, please, we'll go ahead and we'll execute this sequence, and we'll get to the next video, which is going to be the composition, the data acquisition and the composition of the mosaic, just to make sure that we framed it right. So if you liked this video and you like this kind of content, anything astronomy and all things astrophotography, go ahead, subscribe. When you do, you'll get notifications whenever I publish new content, which continues to be once or twice a week, despite the cloudy nights. And with that, I will see each and every one of you on the next video.